Okay, so again, welcome everyone to our weekly seminar. Today we have the pleasure to have Dr. Titas Chanda from Poland. Actually, this university called Jagiellonian University in Krakow. It's very difficult to pronounce actually. So Titas did his PhD from HRI under the supervision of Aditi Sende, where he was working in topics related to quantum information and many-body theory using methods like DMRG and things. And from there, he moved, I think, a year and a half back to work with Jakub Jagiellonian. So Jakub, we know very well. He's yeah. Okay, thank you.
Yeah.
I think it's very difficult to pronounce for me. So with Jakub and from in Jakub's group, he's a postdoc and been working on things related to non-equilibrium dynamics, many-body localization, and also what he's going to talk about today, which is about lattice gauge theories at the age of quantum technologies. So it will be about Bosonic Schwinger model and how you do dynamics there and what do you see there. Okay. So thank you, Titas, for joining us. As I mentioned previously, that we will have questions in between. So whoever wants to ask questions here or in YouTube, just ask a question or raise your hand or write in chat box. We'll take the question as time permits. Okay, with this, it's up to you, Titas.
Okay. Thank you, Shomo, for this invitation and giving me this opportunity to talk in IIT Bombay in these crazy times. Sitting in our office or homes and via Zoom at least. So today I'll be talking about lattice gauge theories, and mainly I'll talk about our recent result published in this paper about out of equilibrium dynamics of Bosonic Schwinger model. And so this talk will be in two parts. So first I will introduce lattice gauge theories from the perspective of quantum technologies. And then in the second part, I will talk about our result on out of equilibrium dynamics of Bosonic Schwinger model. 1 second, yeah. So by quantum technologies here, I mainly mean quantum simulation, first proposed by Uni Manin and Richard Feynman back in 1990s. So the proposition was that since the nature is inherently quantum, it is quite impossible or quite inefficient to simulate it via classical means, for example, via classical computers. So we need another quantum system to simulate the nature. And so this give birth to quantum simulation. And there is two broader kinds of quantum simulation. One is digital simulation, where unitaries of a target system which we want to simulate are simulated using quantum gates via product decomposition in a quantum circuit. So this is very related also to the subject of quantum computation. And then comes analog simulation or the true quantum simulation, where interactions of a source system, for example, ultra cold atoms in an optical lattice or ion traps or superconducting qubits are tuned so that it can mimic the interaction or the physics of the target system that we want to simulate. And in the past years, so the community has been successful in simulating various theoretical models like Bose-Hubbard model, Fermi-Hubbard model, isotopic Heisenberg model, and even Ising model. And on the last month, even anisotropic XXZ model. So this result is very new, and these models are no longer theoretical, but also have now a practical importance from the point of view of quantum simulation. So this gives the main motivation of this topic about lattice gauge theories in the age of quantum technologies, which comes in the form of this question. That is, can we simulate the gauge theories that arises mainly in high energy physics or particle physics? That is, can we simulate a physics of high energy in a tabletop experiment or not, right? So before going into the introduction of lattice gauge theories, let us move back to very beginning. So let us consider symmetries. So we have global symmetries that we transform the system globally, but the physics remains invariant. So, and we call those as symmetries. For example, we can have translational symmetry, phase symmetry in quantum mechanics. And if the symmetry comes under the transformation under a continuous group, then we have also Noether's theorem, where we can have conserved charges, conserved currents, etc. Now we can go a little bit further and we can ask what happens when we transform the system locally at every point of space and time, and the system, the physics is still invariant under such local transformations. So we call them gauge invariants or gauge symmetries, quote unquote symmetries. So the simplest example will be Maxwell's equations in covariant formalism, where these equations are invariant under these local transformations. But it turns out that these local gauge symmetries are not technically a true symmetry, because there exist so many constants of motion that we can always integrate out some degrees of freedom. And we all know that in the vector potentials, only two components are independent. The rest two are not. So this is just a redundancy in our description. And since it is just a redundancy, it cannot be broken spontaneously, and Noether's theorem will not be applicable. Instead, we will get Gauss law. So to summarize, in case of global symmetries, the physics remain unchanged before and after transformation. Whereas in case of gauge invariance, we address exactly same system before and after transformation. The system itself remain unchanged. Then we can ask, since this is just a redundancy in our description, why we talk in this language? Why not, for example, this, that is Maxwell's equation in usual formalism, right? It turns out that when the system or the theory gets complicated, it is very difficult to work in this language, especially, for example, say in quantum electrodynamics. So we can write a Lagrangian in this language, but it will look very non-local, and we will put too much effort to prove that the Lagrangian is actually a local Lagrangian, right? So we need this type of redundancy just to make our life simpler. And as I mentioned, that gauge theories existed as long as Maxwell's equation existed, so which is mid 19th century, and these are classical E1 gauge theory. E1 because the group under which the transformation occurs is E1 group, and its generalization came in the quantum domain in the form of quantum electrodynamics. Later, non-abelian gauge theories also emerges, which are called Yang-Mills theories. And the standard model of particle physics is also a non-abelian gauge theory with this symmetry group, where E1 cross SU2 is for electroweak interaction and SU3 is for the strong interaction. And back then, perturbative calculations using Feynman diagrams were very successful to describe the physics. However, the perturbative approaches failed to explain the confinement of quarks. So what is confinement of quarks? So we know that quarks cannot be found freely in nature. They are bound to form composite hadrons like protons, neutrons, etc. Right, but perturbative approaches fail to explain such phenomena because this confinement of quarks are inherently a non-perturbative phenomena. That's why we need to address or need to approach the non-perturbative limit of these theories. So in this seminal paper by Wilson, he first formulated lattice gauge theory, where he discretized the theory on an Euclidean spacetime in a path integral formalism. And within few months, in another seminal paper by Kogut and Susskind, we also have the Hamiltonian formulation of lattice gauge theory, right? And by discretizing the space and time in an Euclidean space and time, we essentially ruled out ultraviolet divergence. And this opened up new possibilities to approach non-perturbative limits. And since then, quantum Monte Carlo has been very successfully used to unravel the high energy physics. However, we all know that in quantum Monte Carlo, there is a severe sign problem whenever there are chemical potential. For example, this is the proposed QCD quantum chromodynamics phase diagram. We have chemical potential of quarks and we have temperature. And only in this shaded region, quantum Monte Carlo can be applicable. Whereas in these regions, we have sign problem. So it turns out that still at this day, we have various open problems in this subject. However, these things are going on from 1970s, and these theories are from particle physics, high energy physics. So for a low energy physicist like ourselves, why we are interested in this subject? The answer I have already mentioned, that is quantum simulation, both digital and analog. The question is, can we simulate these physics in a tabletop experiment or not? And the first positive answer came out in this paper, where Schwinger model, that is quantum electrodynamics in 1+1 dimension, fermions coupled with electromagnetic field in one spatial dimension and one time dimension, was first simulated in this paper with a few qubit quantum computer digitally. And Schwinger mechanism of pair production was first observed first time in the laboratory. So what is Schwinger mechanism? So Schwinger theorized that if we shine a very strong electromagnetic field, then vacuum becomes polarized and pairs of electron and positron will pop up. But in practice, we need a very strong electromagnetic field, which is not possible in any earthly manner. However, using quantum simulation, we can mimic or observe this mechanism in laboratories. Sorry. Now the problem is, this is digital simulation, and we cannot really scale and this type of simulation with system size properly. So we need the analog simulation also. And in recent times, new experimental results and propositions are coming out for E1 theories in case of analog quantum simulation. And our long-term goal is to simulate non-abelian theories in a scalable way, so that maybe in 100 years or so, we can actually perform this kind of experiments that are only seen in LHC or big colliders. So we can simulate these experiments on a tabletop setting in a closed room. So this is a long-term goal, but we have to start at some point. And in this recent review, so one can find the up-to-date results about experiments, experimental propositions. So this is very recent. So if anyone is interested, please look at this nice review. Then there is another reason why we are interested in.
So Titas, there is a question.
Yes.
Vikram is asking, what is the observable in digital simulations that tells you that there is vacuum polarization?
Okay, so in such digital simulation, you can actually calculate particle numbers, right? So you can simulate the unitaries and operators in a quantum circuit.
Mm-hmm.
So, and you can measure the local expectation values of particle numbers.
Okay.
So that will tell you the vacuum polarization in a time evolution.
Okay, hopefully that answers Vikram's question. Yes, one.
Okay. Maybe when I continue with my results, I can also talk about that.
Okay, sure.
Okay. Now there is another reason why we are interested as a condensed matter physicist in these theories, because of the recent developments in tensor network methods. These tensor network methods has been very successfully used in coordinate matter systems, and it has various advantages over standard quantum Monte Carlo problems. For example, it can work in Hamiltonian formulation so that we have access to a state or wave function. That is, we can assign a state or wave function to an underlying quantum field theory. And as a result, von Neumann entanglement entropy is accessible and it is almost free to calculate. And the main two advantages is that there is no sign problem in tensor network methods, and tensor network method can simulate real-time dynamics, which quantum Monte Carlo cannot. So tensor network methods are really advantageous over in these cases. And in the past couple of years, fermionic Schwinger model, that is quantum electrodynamics in 1+1 dimension, has been successfully studied in various papers. So the list is not complete, and it worked perfectly where quantum Monte Carlo failed. And there are also studies in non-abelian gauge theories in 1+1 dimension. However, in higher dimensions, for example, in 2+1 dimension, there are some advantages using PEPs, but PEPs are very hard to calculate computationally. However, tensor network communities in recent days are trying their hard to minimize such computational cost. So probably in near future, we can do lattice gauge theory problems using PEPs in 2+1 dimension also, and probably very soon also in 3+1 dimension. However, there is another way forward, that is we take the best of the both worlds, that is we do Monte Carlo using tensor network. So that is another way forward. And all of these numerical results are also described in this recent review, if anyone is interested. Okay. Now let's get a little bit technical. So, and ask ourselves the question, given a system, how do we make it gauge invariant? That is, how do we gauge a system? The answer, the simplest answer is via minimal coupling. And how to do it? So in continuum, we just replace the usual derivative via the covariant derivative in the Lagrangian. Here Q is the coupling strength. In QED, it will be electronic charge. A describes the field corresponds to gauge bosons, and tau are the generators of the symmetry group. In case of E1, it will be just 1. For SU2, it will be Pauli matrices. SU3, it will be Gell-Mann matrices, etc. And as an example, so the kinetic term of the Dirac Lagrangian will be just transformed like this. So if we replace the Dirac kinetic term of the Dirac Lagrangian by this, we have a gauge invariant theory. Plus, we can add gauge invariant interactions among gauge bosons. Now, how to do it on lattice? Say we have a Hamiltonian picture. And for now, let us consider only nearest neighbor tunneling. So say we have two sides here and here, and we consider this type of gauge transformation, where Vn is a unitary matrix under some group. The problematic term here is this nearest neighbor tunneling, because it transforms like this. So it has an extra term here. So it is not gauge invariant now. So we have to make it gauge invariant. And again, we do minimal coupling. Now in this case, we introduce an extra field or extra degrees of freedom in between two lattice sides, right? And we replace this kinetic term via this term, where this U is a unitary matrix or unitary operator that sits in the bond between two lattice sides. And U transforms like this. Now, as a result, under this and this transformation, so this and this transformation, the new kinetic term is now gauge invariant. It does not change. So this is the minimal coupling in the lattice picture.
Sorry, what is this U in K cap? So this is just another site. I can think of it as an extra site in the...
Yeah, so you can also think like extra degrees of freedom that sits in the bond between two sides.
I see. It's a bond degrees of freedom that.
Exactly.
And then under the U1 symmetry, this construction will remain invariant. That's right.
Yeah, any continuous group. So Vn can be a member of any continuous group. So here I am talking about only continuous group. For a discrete group, it remains almost same, but U will not be a unitary operator. It will be just a ladder operator.
Okay, so for instance, like Z2 and this kind of.
Exactly. So for Z2, it will be like sigma X.
Okay.
Yeah.
Okay. Thank you. Yeah.
Okay. Okay. So this is the procedure to make a Hamiltonian in a lattice gauge invariant. Plus, we can add some gauge invariant kinetic and interaction term for the gauge fields itself. So this actually summarize the introduction of lattice gauge theories from the perspective of quantum simulation. Any question till now?
Not I see anything.
Okay. Perfect. So let us move to our result on out of equilibrium dynamics of Bosonic Schwinger model. So out of equilibrium dynamics are very hard to simulate numerically. They are impossible in quantum Monte Carlo calculations, at least for these gauge theories. However, the tensor network method shows us a way forward. And these out of equilibrium dynamics are very important because we want to answer the questions such as the existence of new phases of matter, the presence or absence of thermalization, etc. And in Bosonic Schwinger model, the matter particles are also bosonic. And it is interesting because already many works has been done with fermionic matter, but not so many with bosons. Whereas in ultra-cold atomic experiments, bosons are much easier to realize compared to fermions. So from the experimental point of view, considering bosonic matters are very important. And also, there are several papers that shows that replacing fermions by bosons can give rise to new interesting physics. So in our work, we use tensor network simulation in 1+1 dimension. That is, we use matrix product state answers. And to find the ground state of the system, first we use two-side density matrix renormalization group, that is DMRG. And then we perform also one-side variational optimization, which is also called one-side DMRG, to find the ground state. Then for time evolution, we use state-of-the-art hybrid time-dependent variational principle, that is TDVP, for this time evolution. Why it is hybrid? Because we first use a two-side scheme to increase the bond dimension of the MPS dynamically during the first few time steps, as long as the bond dimension of the MPS is not saturated to a certain value. And then we move to the one-side version of TDVP to minimize the error due to truncation. So this is our numerical techniques, and our goal is to
just Titas, one small thing, technical thing. So using this TDVP and hybrid version of it, what is the time scale that you can achieve? Means how long you can propagate when?
That depends on the system. I mean,
or your system, I mean.
Exactly. So yes, so that also depends on system parameters in that case, because it highly depends on the entropy growth with time.
True. So that's
exactly.
Keeping that in mind, let's say I have a system which is thermalizing.
Exactly. So if it is close to thermalization, then I would say for our system size, we can go up to time equal to 40 for lower mass region, lower mass scenario.
40 in the unit of hopping?
In the Hamiltonian unit.
In the Hamiltonian.
Okay, I will show plots for
okay,
that.
Okay.
Yeah. For higher mass, we can go much further because the entropy growth is much smaller. Okay. So our goal would be to find the signatures of confinement out of equilibrium. Now, again, what is confinement? So in this case, so the confinement means that if we separate out the particles and antiparticles, they are strongly attractive in nature. So the particles and attracts more and more if we increase their separation. And we want to find its signature out of equilibrium, because it will be easier to verify experimentally the existence of confinement if it happens out of equilibrium. Because in equilibrium scenario, to verify confinement, we have to calculate several Wilson loops, which are essentially some long range operators and expectation value of some long range operators, and it will be very hard to do it experimentally. But if we find it out of equilibrium, some signatures in the out of equilibrium, it will be easier to see it experimentally. And secondly, we want to show that there is a lack of thermalization and slow dynamics due to the presence of these confining dynamics. Okay, so again, to summarize, so the Bosonic Schwinger model, the original one, describes a Dirac fermions coupled to E1 gauge field, which is electromagnetic field basically, in 1+1 dimension. Whereas the Bosonic Schwinger model describes spinless scalar Klein-Gordon bosons coupled to E1 gauge field. And both are relativistic theory, both are spinless because it is 1D, and semi-classically they have same dispersion relation. And like in quantum chromodynamics, in 3+1 dimension, both theories show confinement. So this is our parent Lagrangian. We have complex scalar field phi for matter and antimatter. Then we have covariant derivatives, where Q is the electronic charge, A are the vector potential, M is the scalar mass, bare mass of the bosonic matter, and F, this term is the usual electromagnetic interaction. And then we discretize it on lattice, and for that we first fix a temporal gauge, that is the time component of this vector potential. We put it 0 in 1+1 dimension. Then we do standard canonical quantization to get the Hamiltonian in continuum, and then we discretize the Hamiltonian on a lattice with a spacing A. And the discretization is done in such a way that matter fields, that is this phi, sits on lattice sides, and the gauge fields, that is this A, sits on the bonds between two lattice sides. Then there are some simplifications, and after those simplifications, we arrive in this Hamiltonian. So this is the qualitative picture, how it looks. So we have these lattice sides, red and blue dots. So red dots say represents particles, which is represented by the operator A, and blue dots are say antiparticles given by B. And in between two lattice sides, we have this wiggly line, which represents the electric fields. So electric fields is measured by the operator L, which is the rescaled electric field. And so in this formalism, it has this eigenstructure with eigenvalues integers from -infinity to +infinity. And U and U dagger are the ladder operators, lowering and raising operators of this eigenbasis. Okay, so in this Hamiltonian, we have first L squared term, which is just the electric term. Then for these bonds, then we have a chemical potential term for the matters. Then we have a tunneling term, which is mediated by the gauge field. So this tunneling happens in such a way that if a particle moves towards right, then the electric field is raised by 1, and if it tunnels towards left, then it is lowered by 1. And the opposite is opposite happens for the antiparticles. Fine. Okay. Now, so this Hamiltonian has a local U1 invariance under this transformation. So if we transform these operators locally, the Hamiltonian remains invariant. And as a result, we have Gauss law generators, which are constants of motion. So these operators commutes with the Hamiltonian. And the physical sector for us is the states that are annihilated by the Gauss law generators. So if we see this equation and this equation, So this is exactly the standard electromagnetic Gauss law in one dimension. That is, divergence of electric field is equal to the charge. So here charge is the difference between particle and antiparticle. And for simplicity, we call it dynamical charge. And using Gauss law, we can also integrate out the gauge fields for an open chain and using this equation. And this leads to a Hamiltonian with long-range interaction. And in that interaction, we have intraspecies repulsion, that is particle of same type repulse each other, whereas particle antiparticle attracts. So these give rise to our confining potential. And let us have some comment also on the ground state of the system. Say we have a free Klein-Gordon theory, that is, there is no gauge field. Then this is integrable model. We can find the dispersion relation on a lattice, and in continuum, it gives back us our relativistic dispersion. And this is gapless in the massless scenario. Fine. However, in the Bosonic Schwinger model, the excitations are not free particles, but they are bound particle-antiparticle pairs, which we simply call mesons. And due to that, a finite mass gap is generated due to this matter gauge coupling. So if we see this figure, so these are energy levels calculated from de-energy calculations. So we can see that even for massless case, we have a finite gap between the ground state or the vacuum state and the first excited state.
Because
And
there is
yes.
a question.
Yes.
Are there any solvable examples of such 1+1 gauge theories?
Yes, actually. So the Fermionic Schwinger model in the massless, in continuum, in the massless regime is solvable by bosonization. But that is in continuum. So in lattice, it is not.
Okay, thank you.
Okay. Okay. So because of this matter gauge coupling, we have a mass gap, which is always greater than the bare mass of the particles. And the extra energy, that is the difference between mass gap and the bare mass of the particles, arises as a binding energy, which is required to tether these particle and antiparticle pairs into mesons. And since the ground state is always gap, we have finite correlations, and the long-range correlation decay exponentially with distance. And as a result, the tensor network can be used very successfully in these systems. Now, in our time evolution, we first excite the vacuum.
So there is another question. Sumiran, can you ask your question?
No, I just following up on this solvable models comment you made. So what makes the forbid solution on this lattice gauge theories?
Sorry, I don't understand.
So you mentioned that in the continuum, the Fermion-Schwinger model can be exactly solved, right?
Exactly.
But on the lattice, it is not possible, right?
Yeah, so in lattice, it is non-integrable.
Why? Why? What makes it solvable in continuum and not solvable on the lattice?
Okay, I don't have much idea, but in continuum, you can make bosonization of fermions into a sine-Gordon, I think into a sine-Gordon model, probably, I don't know, remember right now. So using that, you can solve it, but in on lattice, it is not possible. If I'm correct.
So
I'm not fully
probably
sure.
some scale. So the lattice spacing might be.
Yes, yes.
I see. Okay, thank you.
Okay. So in our time evolution, we first excite the vacuum of our system via this non-local operator. So what it does, so it creates a particle in say n by 2 minus r position, and it creates an antiparticle in n by 2 plus r plus 1 position. So the particle and antiparticle are separated by 2r plus 1 distance, lattice distance. And they're connected by a string of electric field, which is created via this raising operator. This string of raising operator. So our initial state is this one. So where this is the vacuum or the ground state of the system, and we act with this operator. And here n is just the normalization constant. And semi-classically, this state has an extra energy of this amount over the vacuum state. So this will be a schematic representation of our time dynamics. So at 0 time, we have a particle, the red dot, and an antiparticle, the blue dot, separated at a distance, and they are connected by a string of electric field represented by this yellow line, yellow wiggly line. And as time goes, they spread over few sites, creating charged clouds, and they starts to screen the electric field starting from the boundary. However, due to this confining potential, particle-antiparticle attracts and the string tends to shrink. This string in the string of electric fields tends to shrink, so that the light cone structure gets modified and it bends inwards like this. And if the screening of electric field via these charged clouds are strong enough, then at the middle we can have a string breaking phenomena, and also we can see the existence of string inversion or the anti-string, that is the electric field with different sign, right? And in the boundary of this light cone structure or this modified light cone structure, we can have radiation of lighter mesons, lighter particle-antiparticle pairs, which can break free from the electric strings. And these lighter mesons are not bound to confinement, they can move freely, right? So this creates essentially two domains, two distinctly different domains. So here in the middle, in the core region, we have a confined core where the bosons are strongly correlated. And in the outer region, we have deconfined region where it is populated by freely propagating lighter mesons. And due to this radiation of lighter mesons, the mass concentrated in this region slowly depleted. So this is the schematic representation of our dynamics. Okay, so another thing, so after some time, the system tries to get itself to its original position, like here. So the confined core actually shows a coherent oscillation. So this is the numerical results. So for that,
sorry, Titas, so this thing that you described just now, isn't it almost similar to this Ising model thing? So if you have Ising model and if you have a domain wall,
exactly, because in Ising model with parallel field, the Ising model with parallel field, the excitations are the domain wall excitations, right? And this parallel field actually is a confining potential also, because they cannot move. This domain wall cannot shrink. I mean, there is energy cost to grow and shrink the domain wall.
True.
That's why there we also have confinement.
Okay, so the physics is almost similar here.
Physics is almost similar, exactly.
Okay, thank you. So in that respect, can you write down a simple, like a model which is in a lower dimension, lower Hilbert space dimension, such that it becomes a one-body problem?
No, I don't.
No,
because in Ising model with parallel field is also non-integrable, right?
It's non-integrable, but you can live in the subspace of the domain walls.
Exactly.
And then it's a one-body problem, because then it's a subspace where you are looking at the dynamics only in the subspace. Well, it gives you at least some up to time, some time scale the exact dynamics.
Exactly. So I think it can also have some. I mean, it can be also dealt with such perturbation, but still, I mean, to get the full picture, one needs to consider non-perturbatively. Because in the perturbative cases, you can see essentially the string remains unchanged.
Okay.
That is also possible. Yeah. Okay. So this is our numerical results. So we consider 60 sites and 59 bonds, and the distance between particle and antiparticle, which is measured by R, that is 2R plus 1. So we consider R to be 5. And we observe both gate sector, which is measured by this electric field operator at different bonds. So y-axis is the bond, and also the charge sector, the matter sector, is given by this dynamical charge, which is measured across all the sites, and the x-axis is our time. So we can already see the bending of light cone in all the figures. So this is lowest, massless scenario, and then mass increases downwards. So at larger mass, we can see the almost perfect periodic oscillation of both particle and gate sector. So the confinement is very strong, and there is almost zero radiation of free mesons. And slightly lower mass, say 0.5, we can see the radiation of lighter mesons from the boundaries of this electric field string in both figures, and we can easily perceive that there are two distinct domains. So one is this confined core, and other one is the outer deconfined region. And in the massless region, so in the massless case, so the coherent oscillation is vanished after only one oscillation, only one such confinement. After that, due to large amount of meson radiation, the concentration of bosons in the coherent core vanishes up to, say, T equal to 10 here. So the entanglement dynamics is also interesting. So here we measure entanglement of entropy at every bonds. So this is for our Bosonic Schwinger model, and this is the Klein-Gordon model, which is solvable without this confining potential term. And here in the Klein-Gordon scenario, so from the very beginning, entanglement starts to spread ballistically, and apparently after some time, the memory effect disappears in the bulk. So we can say that the system can attain the thermalization in the generalized sense. It will not be proper thermalization because it is integrable model. So we can have a generalized Gibbs ensemble. However, in the Bosonic Schwinger model, the entanglement pattern drastically modified. So the initial spreading of entanglement slows down as the light cone bends, and it starts to spread ballistically only in correspondence with the radiation of lighter mesons for lower masses. For higher masses, yes.
Yeah, no, please continue.
Yeah.
I will ask the question after this.
For higher masses, entanglement only remains in the central region, and it oscillates periodically. And also, in the massless region, so we had seen that the concentration of confined bosons disappears up to time t equal to 10, say. However, the entanglement leaves a strong footprint of the confinement because it is strongly concentrated only in the central region. So it has a very strong memory effect, and it already shows a signature of the lack of thermalization. Yes.
So the question is from the YouTube by Sai. He is asking, in digital quantum simulations, trotterization is an important source of errors. Can you speak to errors in analog simulation vis-a-vis the results you are presenting?
Exactly. So in analog simulation, the errors will be that how good you can mimic the interactions, right? So how good you can tune the interactions in a proper way.
What do you mean by tuning interaction?
I mean, because so in say optical lattice, you have nearest neighbor interaction, but you have also next nearest neighbor interaction, right? By tuning by tuning this lattice depth, you can make this next nearest neighbor tunneling very small, so that if essentially you can have a Hubbard model, like Bose-Hubbard model, Fermi-Hubbard model.
I see.
So it depends on how good you can tune these parameters to make the interaction as close as possible to the theory.
Okay.
So
I had a question.
yes.
Yeah, Vijay.
I'm Urjit. I missed something, but this light cone bends is a many-body effect, or is it part of the basic dispersion relation itself?
No, it
Single
is
particle.
exactly. So in single particle, so this is the again. So in the single particle picture, so which is mainly the Klein-Gordon free theory. So light cone should not bend.
Okay.
So it will go like usual way. But due to this confining potential, the particles and antiparticles attracts very much, and the electric field tends to bend, tends to shrink.
But so it is in a finitely occupied state, right? It's not in the vacuum.
It is not in the vacuum, yes.
Okay.
So it is a highly excited state.
It's a highly excited. Okay, thanks.
Exactly. So the excitation energy, so semi-classically, the excitation energy will be this, which depends on the distance between the particle and antiparticle pair.
So
And also in
the
the
question, yeah. So there is this question of this trotterization. So that continues. So I asked the following follow-up question. He is saying, will there not be an exponential growth of errors from the ordered evolution of errors?
So in
in trotterization, when you do the trotterization of e to the power ih, so there should be an error that you accumulate in every time.
Exactly. So that's why this digital simulation is not scalable both in system size and as well as with time. So we need analog simulation, as very good analog simulation to simulate this in an efficient manner.
Just to get a feeling, so this trotterization we do when we do MPS time evolution, but using this TDVP, which is a bit different method, do you still need trotterization?
We need something similar to trotterization, but we use actually Lanchos time evolution step. So in those cases, error can be reduced to a great extent.
Yeah. Okay. And hopefully all of this result is checked with smaller time step, so that
actually in TDVP, so we have checked. So in various calculations also, not only this one, but this time step doesn't matter much. So if we convert this Lanchos exponentiation, then this time step error is very, very small, 10 to the power minus 6, I mean lesser than that even. So I mean, so if you take delta t equal to 0.01 or 0.1, the results are essentially same.
I see. Nice.
Which is not in case of TEBD.
Yeah, that's what that's what I'm saying. So the TDVP fundamentally is different.
TDVP is
in terms of algorithm,
exactly,
compared to TEBD.
Exactly.
So just to say that we have around 5 minutes.
Okay, so I will just finish fast. Okay, so there is another thing about entanglement dynamics. Because of the presence of global U1 symmetry, we can divide the total entanglement entropy into two parts. So one is the classical entropy, which is the Shannon entropy between different quantum blocks, and one is distillable part of the entanglement entropy, which is the entropy in between these blocks. And only in the distillable part of the entanglement entropy can be extracted via local operation and classical communication. Whereas the classical part of entanglement entropy can be measured very accurately in experiments. And if we see its pattern, we can see that while distillable entanglement entropy, at least for smaller masses, mimics the pattern of total entropy, the classical entropy leaves a very strong footprint in the confined domain, and it sharply demarcates between the confined domain and the deconfined region. Okay, so this type of signature is this already a very strong signature of confining dynamics. It can be also used in experiments. And so this is my last section, that is the lack of thermalization. And let's get a little bit technical. So by thermalization, we mean that the expectation values of local operators will tend to the thermal value as T tends to infinity. And in those cases, entanglement entropy should grow proportional to the bipartition size for sufficiently long time. And our expectation is that since this confined core has a coherent oscillation and it has a very strong memory effect, it should remain non-thermal, and entropy should not grow proportional to the volume size, but slower. Whereas in the deconfined domain, so it is populated by free lighter mesons, which can move freely to spread entanglement, and so it should, in some sense, thermalize in the outer region. So for that, we study different system size with R proportional to N, so that we inject extensive amount of energy to the initial state, which is required for thermalization. And we can see that for different system sizes, for say low mass scenario, the average entropy in the central region shows almost perfect area law along with time. So another signature of lack of thermalization would be to observe its time evolution, the pattern of time evolution, whether it is logarithmic growth with time or not. However, in the low mass region, so it attains its maximum value very quickly. So in this small time scale, we cannot comment whether it is logarithmic or not in case of low mass. However, for large mass scenario, we can go up to very long time and the entropy grows slowly. So we can study its growth with time. And so we can see that it oscillates very fast because of at higher mass confinement is very strong and the coherent oscillation is also very strong. However, the envelope actually follows the logarithmic growth with time. So this is another signature at higher mass region that this confined core is actually non-thermal. And in the outer region, the entanglement entropy follows this scaling law, where N is the system size and J is the bipartition size, with exponents alpha and beta, alpha being very close to 1. So if we fix the system size, then we can see that entropy in the outer region initially grows sublinearly with system size, like here in this case. Then it is linear in the intermediate values of J, that is, it mimics volume law. And then it becomes a little bit superlinear before saturating into this confined domain, which show area law. So this figure is a large time snapshot of the entanglement entropy measured across different bonds for a little bit larger mass. So here we have a system where in the central region we have entanglement entropy which follows area law. However, outside it is almost thermal. So if we decrease the mass, then it will be more and more thermal. So to summarize, the Bosonic Schwinger model shows very strong confining dynamics and trajectories of the bosons bend inwards, similar to what has been already observed in Ising model with parallel field. And as a result, these asymptotic states are highly exotic and non-thermal. And these states are made of a strongly correlated confined core that obeys area law of entropy and an almost thermal outer region, which is for lower masses. For higher masses, since there is no meson radiation, it stays as vacuum. And there are still some open questions, that is whether such exotic non-thermal states persist at very, very long time or not. But it cannot be answered with our present numerical tools because of the errors in MPS. But it can be answered by next generation of tensor network algorithms or by quantum simulations. And so another open question is the origin of this lack of thermalization or slow dynamics in the confining theories. So we will try to address this at least in some part in our next paper. So thank you. So this work has been done with Kuba Jakshevsky, who is also in our university, with Maciek Lewenstein and Luca Tagliagozzo, who are in Barcelona right now. So thank you. And when this pandemic situation is over, so I would like to welcome all to Krakow. So it is a very beautiful city and very lively. Thank you.
Okay, thank you, Titas, very much. I clap for everyone. Some noises. Thank you for this interesting overview talk. So let's see if there is any question.
So sorry, can I just
Yeah,
so this is Sai. Sorry, I was on YouTube a couple of minutes ago. So I'm sorry, I'm just curious about digital versus analog quantum simulation vis-a-vis the errors, because I'm curious as to how you account for the growth of errors in the simulation. So yours is basically one of these situations where you can actually simulate the result, right? So
exactly.
So it's still okay, but I'm asking, I guess I'm projecting forward. I'm interested in kind of quantum simulations that are hard to do on a classical computer, but that can be done on a the kind of genuine quantum simulation.
Exactly.
To stretch it to that corner. So in that, can you just tell me from, so this is a general question about how analog errors in analog quantum simulation is actually dealt with, because I have some pulse shape and then there is some error in the pulse shape. Now, how do you, what are the theorems associated with it? How do you think about the error? I was just curious if you had a
but
point of view.
I am not an expert of these topics, so probably I will not be. I will not have a better answer for that. So the thing is that so in case of analog simulation, so in these E1 theories, right now I think the community can do only up to a bond. So that is, there are two sides and there is only one gauge field. So that they can do right now, but it is not still scalable yet. That up to that part I know, but how errors are accumulated in these analog simulations, I don't have idea.
Okay, thank you very much. Yeah, I was just curious.
Yeah.
Okay, there's a question by Uma. Uma, can you unmute?
Yeah.
Ask? Yeah.
I'm a little puzzled by talking of Bosonic Schwinger model. You say that the mass gap is non-zero even when the mass is zero.
Exactly.
Okay. First, I find this very puzzling. And by the way, this is 1 + 1 dimensional QED that you are talking about?
Yes.
Is this capital M positive or negative?
It is always positive, because in 1 + 1 the theory is always confining, so there is no Coulomb phase.
Okay,
so it cannot be gapless.
The potential is always a positive potential.
Exactly.
So that bound state will have a positive energy.
Exactly. Yes.
Mm-hmm.
So that's why QED in 1 + 1 interesting, because it mimics the physics of QCD at 3 + 1.
Mm-hmm. Okay, thank you.
Okay, is there any other immediate question to Titas? Okay, so if not, let's thank Titas for this exciting talk. Thank you very much, Titas, for accepting our invitation and for this nice talk.
Thank you for giving me this opportunity to talk.
Sure.